You can start your
Okay, so I'll
introduction.
just introduce the speakers and then give a background. So welcome all of you to the IQTI talk. Today's talk is going to be by Professor Bane Vasic and Dr. Nithin Raveendran. So I will introduce the speakers. So Bane is a professor of electrical and computer engineering and mathematics at the University of Arizona, and he's the director of the Resurrection Laboratory at the University of Arizona. He is an inventor of the soft error event decoding algorithm, and it was a key architect for detectors and decoders for Bell Labs data storage read channel, which was regarded the best in the industry. So he has extensively worked on low density parity check codes, worked on the ontology of trapping sets, etc., and designing efficient decoders to overcome the limitations of these trapping sets. He is a founder of CodeLucida, which is a startup, part of the Arizona venture, and I think have learned that this is now partnering with Xilinx, and it provides LDPC codec IP cores for flash memory controllers. And CodeLucida has received many innovation awards as well. Bane is a IEEE Fellow, Fulbright Scholar, Da Vinci Fellow, the past chair of IEEE Data Storage Technical Committee. He is decorated with many honors, and currently he is behind the workforce technical advisory committee within the Quantum Economic Development Consortium, which is part of NIST as part of the Federal Strategy for Advancing Quantum Information Science. He is the PI on several projects related to quantum information sciences, funded from the Fermi National Laboratory, as well as involved in the centers, in both the centers, I think one for quantum networks and other is for superconducting materials and systems. So we welcome Bane to IQTI talk. It's a pleasure to have you here. So Dr. Nithin Raveendran is also going to be presenting as part of this talk. So he's a postdoctoral research associate at the University of Arizona. He did his PhD with Professor Vasic's group at the University of Arizona. His current research area is in quantum computation and communication. He is an alumnus of IAC, and welcome Nithin. So to your alma mater. Okay, so welcome both Drs. Vasic and Raveendran. So the floor is all yours. So Bane, would you mind taking questions in the middle? It's fine. We can have an interactive.
Yes. I don't know how to check questions in chat, but maybe the audience can just ask and interrupt me, so it's fine.
Okay, great. So we have this chat window here. I think some of us will notice that in the chat box, and we will alert you if there are questions, and people can raise their hand, and I will. They can unmute and they can ask questions, so we can have this interactive. So, okay, sounds great. I think we can get started, and a warm welcome to both of you to the IQ.
Thank you, Sean, for the introduction. Before I start with the technical part, I want to say that we have been collaborating with Cheyenne and with Indian Institute of Science for a long time. So we had the Center for Indo-European Center for Data Storage. I think all of Cheyenne students visited my lab maybe several times. I came to India twice. So I started the quantum project. Cheyenne taught me a lot about quantum. So it was just fun project. I started this, I'm a classical coding theorist by my education, but I started learning quantum mechanics, I don't know, 5 years ago. So it turned out that, so we know mathematics, so we can get quantum mechanics, and coding theory turned out to be pretty significant there. And many of these things that are done in error correction for quantum systems is something that we already know. And there were some also very cool and interesting problems that got us curious, and this is how everything started. So it happened that this expertise that we have in LDPC codes is important, because LDPC codes, as I'll show you, are very attractive now. So we have this new Center for Quantum Networks that is hosted at the University of Arizona. So, and we are also, Nithin and I are also members of the Center for Superconducting Quantum Materials and Systems. This is a Fermilab center. And we also have a project with NASA as a part of NASA Strategic University Partnership. So what I will do in this talk, I will try to go and motivate the problem, maybe introduce some effects that are happening in the in LDPC codes when they're used for quantum applications. And then I'll let Nithin talk about technical things. This is, by the way, his work on, and this is published on this archive paper. So I wanted to give this, I actually gave this talk at NASA recently for in Dariush's group, and we prepare it so that it doesn't require too much quantum mechanics background. So we'll start classically. So imagine in quantum computers typically use some kind of a surface codes where you arrange qubits physically on some kind of array, and then you prepare the quantum state, some entangled states, but in a specific way where only neighboring qubits interact. So then what you can do if error happens, and of course errors happen in quantum qubits, then you can detect and correct errors by measuring these local stabilizers. So this red and blue dots denote these stabilizers. And then as you know, these stabilizer measurements are not going to distract the state, and based on the syndrome, based on these measurements, you can proceed and try to correct errors. So the reason that I draw this is because you can immediately establish correspondence between these surface codes and LDPC codes. So in a way, surface codes is just a special case of an LDPC code. So what we do is imagine that we have qubits that are labeled from V1 to V6, and that they are involved in this stabilizer. So this will be X checks, and this will be Z checks. I will tell you more about this. But it doesn't matter even for now what they mean. They actually mean that one matrix is used to correct one type of poly errors, another is used to correct another type of poly errors, basically X and Z errors. But I'm not going to even introduce these errors. So there will be, of course, the errors are quaternary in quantum systems, but we are going to represent them as binary vectors. So this is what we have. So in principle, LDPC code for quantum is defined by these parity-check matrices and by this what we call the Tanner graph. So this basically means that if there was no error in qubits, that these parity check equations will be satisfied. This means that XOR of these bits, binary values, should be equal to 0, and the same thing for these blue checks. So this is the object that we will be working on, this Tanner graph. So we will assume that we have some number of qubits that are involved in this parity check equation, these stabilizers, and our goal would be to find error pattern and correct this error pattern by modifying the state. So why quantum LDPC codes? Even from early work on Gottesman, it was shown that they are important for fault-tolerant quantum computation. But secondly, they can be decoded efficiently using low complexity iterative decoding, and this is very important because to meet latency and power consumption requirements. We will be correcting maybe superconducting qubits that sits in a refrigerator at around 0 kelvins. There will be maybe some wires coming outside of this refrigerator. We will have outside block, maybe FPGA or ASIC circuit to correct these errors. And we have to correct errors quickly enough before new errors accumulate. This fact that they have parity checks of bounded and low weight is important. As you remember, in the surface cost example, only a small number of qubits were involved in a stabilizer. So this is the main property of quantum LDPC codes. Even though we will increase the length of the code or number of qubits, still the number of stabilizers each qubit is involved will stay constant, and the same thing for the weight of stabilizers. So this is what is attractive for in code in LDPC codes, but the main breakthrough came recently this year, and this year witnessed surge of papers in quantum LDPC codes, and it became very hot topic because initially, because of the constraints that quantum LDPC code imposes, and I will talk about this soon. It was, they typically are constructed using two classical codes, but then these two classical codes also have to satisfy some additional properties, and because of this, the flexibility of designing the code is not as great as in classical, and the minimum distance increase with the length of the code, which would be ideal to be, let's say, linear, was not linear. It was a square root of the length. So this was, of course, bad news for quantum codes, but recently, as I said, Panteleev and Kalachev showed that by using some kind of expanded argument, similar that we used for classical codes, that there is a class of codes with the minimum distance increasing linearly with the length of the code, and this made a big push to work in quantum codes. So there is, of course, problem of constructing codes, and this is also something that we are working on, but the problem of decoding of LDPC code is still open. So there are a lot of decoding algorithms that people are discussing. Many of these algorithms are really modifications of classical algorithms, but what is important is that because of the structure of the code, since we will be using iterative decoding algorithms, quantum LDPC codes suffer performance degradation due to convergence issues. So in other words, the decoding problem is this: you measure these syndromes, and you want to find an error pattern that matches this syndrome. And then you are doing this iteratively. But in principle, as we know from LDPC codes, the decoder can try different syndromes, pass messages, and I will show later, but eventually maybe it doesn't find the syndrome. And this is this problem that we call the error floor. And what is important that whatever decoding algorithm we used, message bit flipping, belief propagation, mix-up, and their variants, there will be problem of error floor. Sean, you wanted to say something?
Yeah, Bane, we have a quick question from Pranav. The question is in the chat. So do the two classical codes have to satisfy the CSS criterion? So is the dual containing code satisfying the CSS condition, or do you have a non-CSS?
Yeah. So I have slides. So the next couple of slides are related to this, and I will formulate this. So we, in general, we consider CSS and non-CSS codes, but in these talks we will be talking about just CSS codes. So maybe before this, I tell you, this is basically advertisement to list this project and say that we have a lot of opportunities for graduate students and for research. So these are our quantum related projects. The reason that I'm telling you this and kind of interrupting the presentation is because this iterative decoding of LDPC codes is important in many of these applications that I'm listing. So this is a NASA project tries to design, to optimize these decoders using neural networks. And this is not, by the way, just naive use of neural networks that you sometimes see in the papers. We used neural networks for optimization of decoders, but we realized that if you do classification of images, you will need probability of error of 20%, and you will be happy. In this case, we are happy with probability of error of 10 to minus 15, and the training and everything else has to be defined in a different way, and some important sampling methods are used. So this is the first project that we started and where Nithin was working. This is a new project with Duke, with C in CSS code, with Rob Calderbank and Henry Pfister and Narayanan and Saikat. And this is also a project with Saikat on our research center, and as I said, Fermi Lab project. And for the classical projects, we also have this project of learning to correct errors, which is more fundamental approach to neural networks and in decoding, and these two other projects. Okay, so now back to the question. So we have this XZ and HD and HX parity check matrices. So we define stabilizer code. We define stabilizer code by this matrix. So each of these are n times n matrices, so the total length is 2n, and they have to satisfy this condition. So far, we are not going to go into the reasons why this condition needs to be satisfied. It comes from the fact that stabilizers need to commute. So our channel is depolarizing channel. This means so you see there are n. The length of the code is n. So error vectors will be also of length 2n. So there will be two parts. Part that corresponds to x errors. So this is binary vector, and this binary vector corresponds to z errors. So each of them are of length n. If in case both X and Z error happens, then we have Y error. But again, this is a depolarizing channel, and we assume that errors, X errors and Z errors occur independently with probability alpha. So what we do is correct independently errors, X errors and Z errors. By the way, this is not the case always, so we also consider decoders when there is correlation and when we correct them together. So in other words, where these vectors are not just separated into two binary vectors, where we consider quaternary vectors. But for now, let's consider just this case. So the job of our decoder is to accept the syndrome that is measured and produce an estimate of an error vector with the knowledge of H, with the parity check matrix. So now, to simplify things, we are going to consider this class of CSS codes, and we assume that, you know, as I said, that we are decoding X and Z errors separately. So we'll have these two these two matrices, and they have to satisfy this property that follows from the property here. And so we will have two separate decoders. And even more, what I'm going to do is to, for this sake of illustration, is to consider now the case that we have that both HX and HZ are equal, and this means that our code is dual containing. So this is what really is important here, that now codewords of our code includes the row space of a parity check matrix. This means it's dual, but also some additional codewords. And so if I look at the generator matrix, I will have, you know, this its parity matrix and some additional rows that define operators on an error vector that will result into something, you know, non-trivial. So maybe I can say something. So maybe we do this example, and I think people are familiar with this example. So let's suppose that we look at the Sting code. So the Sting code, this is a generator matrix of the Sting code. This is a parity check matrix. So and you can see the generator matrix contains the parity check matrix and plus this additional row. So these are code words of a dual code, row space of H, and the code words of C contain actually code words of C, but also last row of G plus code words of C. So this basically means that we have, I don't know, two groups of code words, and this is what I mean. So these all code words are in the neighborhood of all zero code words, and all these code words are in the neighborhood of this code word. And by the neighborhood, I mean the neighborhood by when I add this row space of H. So in other words, the code space is divided into two pieces, into two cosets. And now now our errors can be separated into two groups. So for example, if suppose that our state of the system is 0, and let's say if any of this error happens, it will be still okay. This is not going to produce any error. But if any of these error happen, then the state of the system would be translated from logical 0 to logical 1, and this is not going to be correctable error. So now, of course, in addition to these are actually not errors, and if these code words, these errors appear, they won't be detectable. In addition to this, of course, there are other errors that we can correct. So what is important to see in the setting of the problem is that instead of, in classical work, we always have channel information and we are trying to find the code word. In setting for quantum LDPC codes, we are trying to estimate an error vector. So this error vector could be, as we saw in the raw space of H, and in this case it is not harmful, and it can be some of these rows of generator matrix in which it could cause logical errors. But let's set up the problem. So let's E be some non-zero vector that results in the syndrome S. So as opposed to classical syndrome decoder that tries to find for a given observed syndrome a valid output, quantum decoders tries produce any of these vectors. So you see it can produce E, correct vectors, but also any vector that is E plus row space of H, and this will be a valid output. It is valid output because this H, this row space of H are our stabilizers, and they are not affecting the state. And of course, if we have, if the error vector corresponds to the row space of L, these are these additional rows in the generator matrix, then we create a logical error. And this, there is nothing that we can do. So now our goal, after we set up this problem, is for a given syndrome, we want to use a parity-check matrix of LDPC codes and do iterative decoding. So in order to do this, I'll do this example on a Tanner code. So let's say I'm trying to correct one type of errors, either Z or X errors. As we said, we do this independently. So this is a Tanner graph, and this corresponds to positions of error vectors. So this is, each of these corresponds to some element of an error vector, and these are parity-check equations. So if there is no error vector, all these parity-check equations will be satisfied. In other words, XOR of corresponding binary elements will be 0. But let's suppose that we have some errors, and these are these red circles here. Then some of these parity-check equations will have value 1, or I will say they are not satisfied. So now the goal of an iterative decoder is to observe these red squares and place red squares in circles so that they are consistent with the values of check nodes. So obviously, for this arrange, so the decoder, of course, doesn't see this, doesn't have the information of the error vector, and based on these red squares, it tries to position purple color circles. As you can see from the definition of our decoding problem, this is not a unique combination. There will be many more, and this number of combination, as you remember, any combination of errors plus raw space of H will be also a valid error vector. So now we are trying to, of course, find one that is any one of them. So, and we want to do this by iterative decoding. So what we are going to do in this talk, I will try to go over this example quickly to give some time to Nithin to describe our results. But we are going to explain on an example what trapping set is. And then what we want to do is to understand trapping set in the syndrome decoding setting. And then the main our result is that what we'll need to discuss is that in quantum LDPC codes, there are two types of trapping sets. One are classical-like, and one that are totally new, something that we haven't observed before. And then at the end, Nithin will talk about using trapping set to design better codes and better decoders. So let's go over this example. So what I want to do is to describe Gallagher-B algorithm for the syndrome setting and show what messages are passed. So what I would like to do is to define a rule based on which variable nodes, these circles, send messages to check nodes, and in which and rules for updating these check nodes and how messages are sent. So the Gallagher-B really starts from a syndrome, and in different iterations sends messages from variable nodes, from circles to squares, and back to squares to circles, and continue to do this in multiple iterations. And after every iteration tries to estimate the value of the circle, of the bit. So here is a simple rule that we will use. Variable node will accept from different check nodes their messages. So these are messages that are sent from these check nodes, and the message that is sent to this check node will be majority. So in this case, there are three red arrows indicating that they are saying that that these are not satisfied maybe, and these red values will be, this correspond to binary zeros and ones. So when there is majority, then we send the majority value. When there is no majority, we send zero value. So we send zero value because we are trying to find minimum weight error pattern. Which is most likely error pattern. So this is why this slight asymmetry in the rule. And for the rule for the check nodes is that check node sends the XOR of incoming messages plus its value. So in this case, it will be 1. So the check node tries to make number of red colors even. And in this case, you see there were 3 red, and this is red. So you can think of this as XOR of ones plus value 0. So see, this is and the decision is decision for a value of the error pattern and this variable node is based on a majority of all incoming messages. Okay, so you see, this is a very simple rule, and I will be spending time to explain this effect of this rule on trapping sets because it is simple to see. But what we have done with Nithin, we didn't consider Gallagher-B algorithm. Our decoders are more complicated, and Nithin has developed, in addition to this work on trapping set, another method to enumerate trapping set for more complicated decoders. But we can talk about this maybe some other time. And I said our decoder is simple, so it sends these messages. So let's suppose that we have a large graph, and let's suppose that in this graph everything is correct, but it just happens that there are 3 errors in these variable nodes. And of course, there are more connections to these check nodes, but I'm not showing them because they're not important. They are, they are connected to all satisfied variable nodes, and the messages from these variable nodes are always correct. They're always 0 and don't affect anything. So now you see what we observe is this syndrome, and you see all these parity check equations are 1. Or unsatisfied. So our goal is in a decoding algorithm is to find this error pattern. So this is how we start. We initialize decoder with all 0 error pattern because it is most likely error pattern that can happen. And then we start message passing. So we send these values 0 to all check nodes. And then in the second half of the iterations, we propagate messages from check nodes. So for example, you see this check node here will propagate red message to this variable node because it receives one white message and it itself is red. So you see, these are all messages that are checked from check nodes are red to all variable nodes. So now when I want to do a decision, remember I take majority of all incoming messages, what do I decide? I decide that this is error pattern. And remember, this is not correct error pattern. And we know that it is incorrect because now we have the syndrome. When we compute the syndrome, you see that only all these parity checks will be 1 and this parity check will be satisfied because it is 1 plus 1 here, and this one is satisfied because it involves 2 variable nodes that are in error. So this is a syndrome mismatch, and we say that we haven't found error pattern, so we continue. So, by the way, in most of the cases when we write an iterative decoder, it will be able to correct a lot of errors. But you see, this trivial, kind of innocent-looking graph is creating some problems. And you will see that the problems are even bigger. So now I continue this process, and I don't think that we have to go over this over iterations. But if I run the animation for what messages are passed in the second iteration, you will see that basically whatever was sent in the first iteration continues to be sent in the second iteration. So you see, in the second iteration, actually, we send this once, and majority here becomes 0. So in the end of second iteration, we actually think that there is no error pattern, that everything is correct, and all check nodes seems to be satisfied, but they shouldn't be satisfied. We know that this error pattern doesn't match the syndrome, and the syndrome values are, as you remember, these values. So we haven't converged, we continue sending messages, but you see this scenario, what we see here, it looks very much on how we started. And basically in the next iterations, we just continue repeating the same messages. So therefore the decoder didn't converge. And you see, we can design a very good code with a very large minimum distance, but presence of this kind of graph is going to create convergence issue. So what we want to do is to study these kind of configurations that lead to, and we call them trapping sets. So what is important to notice is that whether a decoding algorithm produces a valid correction vector depends on weight of error vectors and minimum distance, but also depends on the vector itself and the decoder. So in other words, it depends on where this vector is in the graph, whether it belongs to some neighborhood, it is placed on some neighborhood that is dense, and of course it depends on the decoding algorithm. So for codes on graphs, ability of an iterative decoder to correct an error pattern is determined by specific topologies in the Tanner graph that we call them trapping set. And error floors is, so this is typical behavior of iterative decoders. So this is a depolarizing probability, and this is frame error rate, probability of the codeword error. So what will happen is that, of course, when we have large probability of error, we cannot do well in the decoding. When this probability decreases, we are better and better. When you would expect that this improvement in decoding performance will continue, but because of trapping set, there is this effect that we call error floor. So this error floor is attributed to the convergence issues and this trapping set, and this is what we are trying to find. By the way, I don't have any plots for quantum codes, but for some quantum codes, this error floor is really bad. It can be like on 10 to minus 2. So this is not the regime where we want to operate, and thus it is of critical importance to reduce it down. Nithin, maybe you can continue now, and I'll change slides, and then you can talk about what we found about trapping sets.
Yeah, that sounds good to me. And so I'll basically indicate to change the slides, and you can change the slides. Thank you. And yeah, thank you, Prof. Vasic, for basically clearly motivating the problem, problems which arises essentially when we try to decode quantum LDPC codes, and also for illustrating what a trapping set is with a simple example using the simple Gallagher-B decoder. So yeah, I'm excited to give this part of our talk. Now I'll try to, in the subsequent few slides, I'll try to explain our work and what results we found, especially on what are the types of trapping sets which are observed in QLDPC codes, and also try to emphasize what is non-classical, or what are the interesting things which we observed when we analyze these quantum trapping sets, quantum LDPC codes and their trapping sets. So next slide. Yeah. So for simplicity, we'd like to keep the definition of a trapping set very similar to what the classical trapping sets have. There has been extensive work since the 2000 on enumeration, classification of trapping sets, and like using trapping sets to create better codes and decoders for classical LDPC codes. So what we did essentially was we adapted the definition of the classical trapping set for fitting the syndrome decoding scenario. That is, if we don't have eventually correct variable nodes in eventually correct variable nodes, and that would essentially mean that the error patterns or the decoding algorithm has not converged to match the particular syndrome. So we essentially are fitting the classical trapping set definition to fit the syndrome decoding scenario. So we essentially keep the A, B notation. What I mean here is that when I describe the trapping set, the same example as Prof. Vasic has shown, here we have 5 qubit nodes or error nodes, or variable nodes, and the subgraph which it forms has 3 odd degree check nodes or unsatisfied check nodes. So that is called an A, B or a 5,3 trapping set. So, but yeah, so this is a summary. Okay, go ahead, please. So this is a summary of our findings. As a summary, we observe these 2 following problematic structures. So first one, as we observe in the classical trapping sets, it's very classical-like trapping sets, and these are caused due to dense subgraphs. That is, when I mean dense subgraph, it is a combination of more than one cycles, and this essentially causes the iterative decoder to fail to converge, just like the example what we saw. So we have the 5-3 trapping set, and basically the decoder gets trapped in these cycles and is not able to converge to the correct error pattern. The more interesting part is the second type, which is the inherently quantum stable trapping sets, which is essentially caused due to the symmetry of the stabilizers. So, so this, you can see that there is no unsatisfied check, or there is no stabilize, so there is no square node which is colored in black, right? So this is essentially causes this we call as NA, 0. For example, here it's a 10, 0 trapping set. Essentially, this is the graph of a stabilizer in the code itself.
So, Nithin,
So why
I have one
is
quick question here. Inherently,
yes.
quantum trapping set. So, is it? I mean, what is the symmetry of the stabilizer in terms of the operator? The stabilizer is an operator, right?
So yeah, so stabilizer and operator,
what
but
is the symmetry here?
So symmetry, what I'm okay. So I'll explain this in the next subsequent slides. But what I mean is that the error patterns, which we can introduce in the stabilizer, that if there is an equivalent, okay, I'll talk about the example of the degenerate error pattern. So for example, in the same stabilizer, suppose we put the errors on these red locations. Okay. So when we have errors on the locations, we have all the checks on in this stabilizer flagged as an error. Those are the unsatisfied checks. Now, so there exists essentially is an equivalent error pattern, which is denoted by the blue, which has the same stabilizer syndromes essentially. So the syndrome flagged by both of these red and a blue error pattern is essentially the same. And now what happens is that the decoder, so for both the red error pattern and the blue error pattern, the decoder essentially competes in the message passing algorithm. So which is the candidate error pattern for an iterative decoder? This is essentially true when for next slides, please. When we have both these error patterns, red and blue, which basically together they induce the subgraph of codeword, which is a stabilizer. So the iterative decoder, what happens is that they have very symmetric rules in both the check and the variable nodes. And the decoder essentially tries to converge to both E and F simultaneously. And that is essentially leading to the decoding failure. So this is what I meant by using so when we use symmetric decoding rule and also a graph which is symmetric, we can have the iterative decoder just stuck because of this symmetry. Okay.
Yeah, so if I can add, so you see, earlier we had this conclusion that the problem of decoding is kind of relaxed because any error pattern, it is not unique error pattern, that we can have any error pattern plus, row space of H. But this choice that now have, because of symmetry of the rule of the decoder, can create problems.
Yes, related question again from Pranav on the same note of degeneracy. So the degeneracy should not affect the quantum code word, right? I think from the results in quantum, right? It is another pattern. For example, short code does it. It's a degenerate code, right? So should this not affect the code word during the decoding? Because, and I have a related question again to the decoding algorithm itself. So post measurement, I think we can think of invoking the message passing algorithm, I assume, because when you think about normal quantum operations that you can think of, and you have these operators directly, and then you can, when you have these errors, basically you would kind of work to undo these error patterns through these operators that you figure out, essentially diagnosing this error. Right, but now I think since you're now invoking the message passing algorithm in the classical setup, are you making measurements inherently there, or is it, or what is the mechanism between this and the?
Yeah, so it is the effect of the fact that we are doing this iteratively. So this comes, as we said, it shouldn't affect, and if the decoder somehow knew it and treats in a different way these two competing error patterns, you will solve it. But remember, the rule for message passing it is derived from belief propagation. It is symmetric, so all messages, the rules for variable nodes and check nodes are all symmetric, and therefore you have two candidates for a solution, and they are treated the same way. And the decoder, by the way, there will be many other error patterns here that could be candidates, but the decoder just cannot decide, and it gets stuck in the trapping set. So now Nithin will show also the remedies for this as well.
So I want to elaborate a little bit more. So the quantumness and the degeneracy property is, as you said, like, it should not affect the solutions which we output. So given a message pattern, and suppose there are multiple error patterns which like satisfy this particular syndrome, the decoder can essentially put out any of these error patterns. So when we have this symmetric structures and a symmetric decoding rule, the decoder is essentially confused to output either the red error patterns or the blue error patterns. And instead of outputting either red or the blue, the decoder essentially is trying to push towards the combination of it, E and F together. So this, I'm saying, this is essentially the why, how we are decoding the quantum codes, which has this additional flexibility of having a decoder degeneracy, but we are doing it naively and using a very symmetric rule. Essentially here, like, goes to a disadvantage for us actually, because it is trying to decode, to converge to both E and F simultaneously.
But what is important to say is that in the code, there will be different stabilizers and different configurations, and most of these configurations are not going to be symmetric. But if it happens that we find one, then we are in trouble.
So this essentially also, so next slide, please. So, okay, here I essentially say why the symmetric stabilizer trapping sets are bad, because whenever there are errors which essentially are split in between the stabilizers, and even when you use very strong iterative decoders, because any iterative decoder which has a symmetric rule will essentially fail here, even so it fails for Gallagher B decoder, Minsum decoder, or even beyond, just because we are essentially using very symmetric rules to decode on these stabilizers. So instead of essentially, if the messages in the symmetric graph is all equal, and the decoder essentially outputs E instead of E or F, we essentially produces the output E and F, and this would not be a valid solution for this problem. So next slide.
So, one more question on a related thread from Shayantan. Will these quantum trapping sets vanish if I want to correct only non-degenerate errors?
Only non-degenerate errors. Yes, for a not. So okay. So where this degeneracy issue comes in is, okay, so we have errors which we can correct, and we have errors which we are unable to correct if it is beyond the minimum distance. So when we are thinking of a non-degenerate code, what we are looking at is codes which have the weight of the stabilizers which is greater than the minimum distance of the code. So the errors which comes in those, if it is beyond the minimum distance of the code, we could as well treat all of them as uncorrectable errors, and it might not be relevant for our performance curves, essentially, in my opinion. And where it comes most important is that even when we use a code, so say a quantum LDPC code has a minimum distance more than 20. And suppose your stabilizer weight is just 4 or 6 or something. What we essentially see is that the decoder, the iterative decoder, will fail for half of these error patterns in the stabilizer, and this can essentially contribute to a very bad error flow. So that's the answer for that question. Yes. Okay, so what is also interesting in these symmetric stabilizers is the harmfulness of the error, harmfulness of these trapping sets, which contributes towards the error flow. For example, when we look at classical trapping sets, and we like say you was using this 5,3 trapping set, which was used in the example. So if you put any error patterns of a specific error pattern of weight 3 or more, that is 3, and then any combination of 4 error patterns or 5 error patterns in that 5,3 trapping set, the decoder is gonna fail. So there is this critical number of errors where you put, and beyond that, any error pattern if you add, the decoder is gonna fail. So we basically determine harmfulness of a trapping set by these two parameters, critical number and strength. So we also count how many of those error patterns fail in these trapping sets. So in these symmetric stabilizers, it is kind of interesting that the harmfulness property is also different. That is, so we can essentially exploit the degeneracy property in this decoding. So so if you consider an a, 0 trapping set, which is in a stabilizer, and suppose you devise a decoder which can correct up to say 4 error patterns. So in classical setting, we would think that anything beyond that is uncorrectable. But in the quantum setting, since we are essentially finding these error patterns in the stabilizer, it so happens that higher weight error patterns can also be corrected. So addressing the issue of the decoder failing in these symmetric stabilizers is very important. So in a sense, if we are able to correct everything so for example, we have a stabilizer of weight 10 here as shown here, and then if we are able to correct everything up to weight 5, the remaining error patterns essentially in the stabilizer is automatically corrected because it just maps to the degenerate error pattern. So what I think the concept of degeneracy is like just that we take two error patterns, E and F, they basically add up to the stabilizer. That's what I mean by a degenerate error pattern. So this is very interesting to see that. And okay, here, and so in this code, so the decoder essentially we found this stabilizers in this 254,28 code. So basically those dimensions are basically n and k for the quantum code. And what we see is that the decoder exactly fails for the 5 error patterns, and it can correct everything below and above the 5 error patterns. And it so happens that when so the decoder tries to push for both the red and the blue error patterns simultaneously in the iterative decoder. And essentially what we need to do in iterative decoder then, if we can identify the symmetric stabilizers, is to break that symmetry. So in the subsequent slides, we'll okay, can we?
So which slide, Nithin?
I would get to go back. Yeah, this is good. So next slide, please. So can you go back one slide? Yeah. So I would like to summarize the decoder, what we just discussed so far. That is, we are looking at the trapping sets, which are both classical looking trapping sets and the symmetric stabilizers, and the degenerate errors, which split the stabilizer, are critical to be corrected for an iterative decoder. So if you're proposing some iterative decoders for quantum LDPC codes, better make sure that we can correct these errors in the stabilizers. So we should, so two things which we can do in the implication of this trapping set is that, so what can we do with the understanding of these trapping sets? The main two things which we can do are, you can construct codes which are free of these small dense subgraphs. And also we can do something to modify the iterative decoder to make some rules asymmetric and break out from these symmetric stabilizer trapping sets. Next slide, please. So one approach would be to not use a symmetric stabilizer. For example, you can change the remove some of the stabilizer rows so that there is uneven weights in the stabilizer, which can essentially push your decoder towards convergence, even in stabilizers, as errors in the stabilizer. So basically, making them asymmetric with respect to some certain axis can help. Next slide. Another approach which is very common in classical trapping set study or classical error correction is to modify your code such that you can eliminate certain small trapping sets during the code construction itself. So, for example, in certain hypergraph product constructions or this recently constructed lifted product constructions, there are essentially two classical codes which act as your component codes. So the trapping sets which we find in one of the classical codes also appear in the quantum code. So you would want to make your classical code as best as possible by eliminating certain small trapping sets, so that they don't essentially multiply and apply or appear in the quantum trapping sets, quantum LDPC codes. So the key point here I would like to mention is that we should not be removing we should be able to determine what are the critical trapping sets or what are the most harmful trapping sets to be removed while doing this code construction procedure. So we propose some solutions in the classical framework. Because we are essentially designing the code in the classical setting and then using that code as the constant code in the quantum world. So in this work, we essentially obtain the list of most harmful trapping sets, and we can find what to remove, and we can essentially construct codes which essentially remove the most harmful trapping sets. As I said, it's not the size of the trapping set basically determines the harmfulness. It is essentially these two parameters, critical number and strength of a trapping set. And these numbers essentially depend upon where these subgraphs are present in the code. Next slide.
So I want to say that Nithin explains it in an abstract way, in a general way, but we actually do this. I mean, we have a software that does all this optimization and search for trapping sets. So it is pretty powerful things that we developed, Nithin developed.
Yeah, so I would like to explain, point out the paper, and if you guys have any questions, I can certainly comment and discuss over that offline. Yeah. So using such trapping set aware code constructions, we can significantly improve the performance of these quantum codes. So they essentially does not have many of these annoying small trapping sets. If we construct the quantum LDPC codes, minimum distance is not just the criterion, especially in the error floor. Especially in the error floor, we need to account for these trapping sets and construct these codes carefully. So the next slide. So I mentioned how we can essentially construct better decoders. Here I would like to say one simple approach where we can break the symmetry in these stabilizer trapping sets. So we saw that the issue when we had this symmetric update rules was that it was pushing towards both the red and the blue nodes, the error patterns together, and it was outputting this just the combination of it, and it was just essentially getting trapped. So the decoder was not able to converge to the correct or match to the right syndrome. So what we can do in this setting to simply break the symmetry is not use a parallel schedule, but instead you can use something called a sequential or serial schedule. So what I mean by schedule is when Professor explained the iterative decoder, we essentially do the variable node update for all the variable nodes, and then the check node update for all check nodes, and that constitutes one iteration. There are other approaches which conventionally used in classical LDPC code, classical decoders, where we use the other schedules of iterative decoding, where we decode sequentially, that is one variable node after the other, and then subsequently doing the check node and so on. So, and there are other approaches where you can use layered decoding schedule. So the decoding, what I want to say is that we can use the asymmetry in that is how the decoder is scheduled to break the symmetric trapping sets as well. So a simple example shown here is when you use a flooding min-sum algorithm, you get the floor at 10 power minus 5, and that can be significantly lowered by using a layered min-sum approach. So this, I would like to say that, so this is one approach where we can use asymmetry to break these symmetric stabilizer trapping sets. But there are other approaches which we also consider to make better decoders, essentially by looking closer in these symmetric stabilizer trapping sets and changing the decoding rules such that we can break these symmetric patterns and push the decoder to one of those error patterns, or any of those error patterns which match the particular syndrome.
And Cheyenne probably remembers our paper on stochastic resonance decoder, where we introduce some fluctuation, some air noise in the decoding algorithm. So this also worked because of it also introduces asymmetry. But now we understand reasons why, why we were failing and why this worked. So now what Nithin is introducing is more deterministic ways to deal with this error force.
So, but the key aspect here is that it is post measurements, right? This is post measurements, right? The decoder, because it's iterative in nature, right? Because you are doing message passing, right? In that sense, it's post measurements that you're reconciling this, or if it's a quantum state and if you're trying to probe there, right, you're going to break that state essentially, right? If you have a quantum code word, LDPC code word, right, in this superposition, right, and directly if you were to put some ancilla out there and then kind of infer, so you can build with this framework that you have operators. That you could devise these stabilizers and you could kind of infer the ancilla, and from there you have a recovery mechanism that you can undo it, right? But if it is a large, medium-sized code, and LDPC codes, at least in the classical case, is very good for large block lengths, medium to large block lengths. So in this regime, if you were to devise these stabilizers, etc., that I think that would be a combinatorially very difficult problem, right? And so what I'm trying to say is, are you going to do a measurement and reconcile this classically through message passing, or you think about a better graph that you devise for this LDPC, and then you work with operators completely in the quantum realm, all quantum realm?
Maybe I'll let Nithin discuss this, but generally speaking, different technologies allow you different ways of handling qubits. So in some, in maybe superconducting technology, it would be difficult to, arrange and make these qubits to interact in a way that you want it to. But in some other technologies, this is not a problem. And and you are right. It would be. It is simpler to do what you suggest, that you interact directly on the space. But here you do this set of measurements, you do processing, and the processing must be very fast. By the way, we just saw, we are writing one paper, kind of survey paper on literature on hardware for quantum decoders. And you can see that there is a lot of interest now, even, big companies like Microsoft and Google start publishing papers on addressing these issues of latency and hardware complexity and etc. So so I think the time has come to consider these issues, and LDPC codes, of course, they need to handle a large number of qubits to be effective, but they have favorable properties in terms of latency and decoding complexity. So I think this is why they are so interesting at that moment, in this moment.
So
Yeah.
I'd like to add.
One is the coding side of it, the other is the decoding part of it, and then the all quantum versus quantum classical interface. And I think you can think of various system level kind of.
So
I think this is at the classical quantum and then post processing.
So the
decoders.
decoders.
I was wondering if you had if you also had maybe if you were to realize this iterative way through some kind of trotter evolution and then figure out something else in that space. I was thinking about your decoder maybe in that realm, but now I think I'm clear. So what is happening here? So I understand.
So Nithin has to answer questions of both his professors now, me and Shai.
It's a good thing to be at this stage. I mean, so it's all right. And I want to add, like, you might be aware of this work from Joseph Rennes about BPQM. It's basically belief propagation with quantum messages. So that is the closest I can think of. Mostly, like sticking with in the quantum realm itself, and it is not for a generic case. It is for basically using. So it's a classical CQ channel, not like all quantum, like like a stabilizer code, but it's for classical classical data, which is now encoded using a binary code. I mean, and they started with a tree code. And it's transmitted over a pure state classical quantum channel, essentially. And then they showed that BPQM, which is basically belief propagation, but using quantum messages, was giving the maximum likelihood. And it actually gives the measures close to or it approaches the Hellstrom measurement after you do the processing. So basically, Joseph Rennes found these nice rules, which essentially map the belief propagation rules for these quantum states. Do measurement, and then you can push everything, like do essentially, you don't do destructive measurements or even the stabilizers, but we essentially do the check node operations and the variable node operations subsequently. So, and it works completely fine for tree codes. And there has been extension of that work recently.
But the tree
also
code is not good in terms of the
so
miscorrection, because I think miscorrection is largely ignored in the coding community, barring very few works. But I think that can become quite critical. When you it could be one of the deciding parameters. Because if you have a tree code, with dangling nodes, I think you might land up with poor miscorrections, right? So, yeah.
I think we kept our audience longer than we planned. So I would, Nithin, anything else, any thing that we will say, or we shall thank our audience for coming to the talk and point to these papers.
Yeah. So like I would also like to point the some of the recent works which we are also doing in the space. Something which we totally swept under the rug was that measurements also are noisy. The stabilizer measurements what we do are also noisy. And in the last bullet, I essentially talk about a way we can use information from the syndrome measurements to use it in the iterative decoder. Okay, it is also post-processing, sort of like do the measurement and do it in the classical realm and push back the recovery operation. But still, like, you can essentially exploit the information from the syndromes and make iterative decoder push closer towards a perfect syndrome measurements. So yeah, thank you for the audience to very interesting questions, and thanks for the invite from ISC as well.
Yeah, I have a simple question. This coding, whatever notation has 3 arguments, n, k, and d. But some of those expressions which you had only 2 arguments. So does it refer to the same system or it is something else?
Nithin, you want to answer?
Yeah, if you go back to the previous slide. Yeah, no, not this.
Do you mean this? This?
Yeah, here the notation is N, L, and D.
Mm-hmm.
And the slide just before your thank you slide had a code which had only 2 arguments.
Yes. Yeah. So basically they are the same. So the N and the L remains the same. It's just that the minimum distance was not computed, and it was just that I did not have the resource at that point to compute the minimum distance exactly. So it's not coming from an algebraic code which I can find the minimum distance explicitly. So I had to do basically a search algorithm for finding the minimum distance. So I revoked
was
that.
Was it a QC code, or it was not a QC code? Is it that 254?
It is a quantum code. It's just it's a generalized bicycle code, and the minimum distance was not obtained from the classical to.
Yeah, maybe you try the Fourier's algorithm.
Yeah. So after that we actually
yeah.
But it's only a bound on the minimum distance. I cannot find it exactly.
Yeah, you cannot. It's NP hard, so you could compute it. So
thank you for the question.
Okay. Yeah.
Any other questions from the audience? So I have one question related to the technological part. So where do you think this LDPC codes, quantum LDPC codes could be used? Maybe in superconducting setup, or maybe for communications, photonic communications? I feel it may be better off in the superconducting part.
It probably was more suitable for communications. And so in our in our center project we are studying LDPC codes. We study different type of algorithm, different type of approaches. So for example, in one example we have this entanglement distillation problem, and then but coded entanglement distillation problem. And for example, in this setting, you can think of using LDPC codes. There are, of course, just more classical kind of setting in which you would correct qubits.
Yeah, in terms of the constraints, what we need to satisfy is so surface codes are essentially LDPC, but they only connect locally, right? So the stabilizers only operate locally. But so I think the photonic platform is as far as I had discussions, they are able to now have entanglement non-locally with these. And they said they are essentially looking at quantum LDPC codes also in their even in the computing setting. So I spoke with companies like PsiQuantum and also Photonic, and they were really interested in looking at quantum LDPC codes and their decoders as well.
That would be great. I mean, because a lot of wisdom that we have from the classical side on the design of these codes, and it's now, if you can kind of work it now in this quantum classical interface, and it's you can turn the hourglass around within the quantum framework, and if it solves the problem, I think it'll be very interesting. Because the conventional quantum codes, I think, have been all in the operator realm, without these algorithms involved, right? In the classical kind of algorithms involved. So I think it'll be interesting. I mean, if you can do fast processing and you have an FPGA board which connects, and you do the measurements, and you're not worried about the nature of the XYZ, and you treat this as an error, and then from there you can work with the classical part, and you can, as long as you can resolve it, it is great. Or you're like a one-time pad that you can send this quantum state, do measurements, and decipher that information. I think that still works on the fly. So.
Yeah, indeed, there is a lot of work for classical coding people. So I'm organizing this. So I'm a co-organizer of the International Symposium on Topics of Coding, former Turbo Coding Symposium. It will be next year in Brest, and there will be one or maybe two special sessions on quantum codes, dedicated to classical audience.
Yeah, that'll be interesting. Quite interesting. Great. I think we are getting close to the end of the talk, I think. So thank you very much, Bane, for a very interesting talk, and thanks, Nithin, for coming in. And it was nice to hear and see you both. I mean, we have interacted through projects and things, and it's a long time since at least we caught up. And again, Sister Web, hopefully we'll be able to see you in physical presence at ISC sometime, and we can initiate collaborations and discussions, and I think we should.
Yes, it was indeed really good to see you, Cheyenne, after a long time.
Yeah. Great.
Thank you. Thank you, Professor Cheyenne, and also stay with you.
Thank you. Thank you so much.
Thanks all, and hopefully we'll be in touch.
Yes.
We should interact.